So let's talk probabilities. Let us assume that you have a bomb which is placed under a huge stack of wood, and you have an explosion and it goes boom. What is the probability that the splinters will fall down and form a perfect little house with functioning windows and doors and everything just immaculate? What is the probability? Well, it's extremely remote. Would you agree? All right. But if you look at science, let's say the probability is 1 to the number of particles in the entire universe. How many atoms in your fingertip? Billions, right? Zillions, billions and billions and billions and billions and zillions. So how many atoms in this room? How many atoms in the entire universe? Wow! How many, not even atoms, particles, protons, hadrons, quarks, neutrons, electrons in the entire universe? Every galaxy, every gas cloud, every planet, every single thing in the entire universe. How many of those particles? I'll tell you, 10 to the power of 80. Doesn't look very big, right? It's a massive figure. The probability of the molecules coming into existence, the probability of the molecules forming life is far greater than even that. So we're not talking boom, little house. We're talking boom, New York City. Do you believe it? With escalators working. No problem. That's the type of probability we're talking about. Dobzhansky once worked it out that from one species to go to another would take 100 generations or 1,000 generations, whichever way you wanted it, with at least 100 or 1,000, either way, point mutations. So that is 100 to the power of 1,000. That is such a huge number, you don't even want to begin, because it's the number of particles in billions and billions and billions and billions and billions and billions for eternity universes. Impossible. Now, science has an easy way of dealing with this. Very easy way. There's a book called The Blind Watchmaker, which says, who cares? The fact is that we are here, therefore it happened. Right? But I just want to show you in this lecture how far we have to go to believe in this process called chance. DNA contains, this is a DNA molecule, contains all the information as to who and what we are. Is that right? And every organism contains that same DNA. Now that DNA we call our genotype. So that's genotype is all the genes present in that first cell. So what comes together from father and mother, that's what we have in our genes, that's our genotype. Phenotype is what you actually are. Which genes are expressed and what you look like. Alright? Let me explain that a little bit more. So this over here is the DNA on the left, that's the genotype. And on the right is what that individual looks like, that's the phenotype. Everybody with me? You know those two words now? Genotype, phenotype? Okay, remember them. Genotype, phenotype. Example. A law in evolution says natural selection operates only at the level of the phenotype. Alright? It only operates at the level of the phenotype. That's the one on the right there. At the level of the genotype, what happens there happens by chance. So at the genotype level, everything happens by chance through mutation. Are you with me? So everything happens there by chance, and at the phenotype level, what comes in? Natural selection. Simple example. Two people walking in the Kruger National Park in South Africa. The one is short and fat. The other one is lean and muscular and powerful, like me, for example. And you're walking along, and a lion jumps out from behind the bush, and you take off like greased lightning. What is the probability of which one surviving? Which one will most likely survive? The lean one. which means that you must always take someone short and fat with you when you go to these dangerous places. Okay, so that's natural selection. It selects between the one that is more fit to cope with that situation than the other one. Are you with me? All right, the lion doesn't ask, excuse me, have you got any other genes in your gene system that haven't been expressed here? He doesn't care. He just cares whether you run fast or whether you don't. Is that right? All right, so natural selection happens at the level of the phenotype. At the level of the genotype, everything happens by chance. Have you got that? Okay. Here I have, therefore, to put it in simple language, a book. And this book we'll call our genotype. The book contains the instructions of how to build aeroplanes. So that is what? Genotype. And once the aeroplane has actually been built, that is phenotype. Now I have a question for you. Who wrote the book? Who wrote the book? You have two chances. It was either chance or it was a designer. Are you with me? Because what happens at the level of the genotype? It's chance. Or you have another option, which is design. All right. So now you have this great book which tells you how to build an aeroplane. And the book is on my shelf. Now, how long will I have to sit and watch the book before the aeroplane actually appears? Well, how long would you reckon? Forever, right? But the aeroplane has to come into existence before I can see whether it works or whether it doesn't work. Are you with me? Yeah. So all the processes that translate what is written there into that take place by which two means? Chance or design. Okay. The probability of the book having been written is boom, New York, New York, New York, New York, New York. Boom, New York, New York, New York, New York, New York. Over and over and over again. For every single gene, I have to assume that this was chance. The mechanisms to make it, also chance. So if we take that to the cellular level, our DNA is so complicated in the way that it is read. I will leave that one. The way in which we take the information of there to the factory, the ribosomes which make the product, the protein, all of it had to come about by chance. Because the final fellow must be there before I know whether he works or that he doesn't work. So now let's say I've written the book and I want to make some changes to the book. Any change that I write in the book, how does it have to come about? By chance, through mutation. All right? So any modification in that genotype to bring about any change in the phenotype must come about by chance. So people will say, well, all these things are mutations, like a lighter animal or a darker animal or a this animal or a that animal. Let's have a look at mutations. You get various types of mutations. Simple one, as an example, would be a point mutation, where you take one of the letters in DNA and replace it. So you have DNA is a triplet code. We have how many letters in our alphabet? 26 letters, and we can use them individually. DNA has only 4 letters, and it uses them in groups of 3. So I can take a letter out, and I can add a letter, and I can get all these things happening over there. Let me simplify that for lay people. So let's make a triplet code, the cat and the hat. And let's say I have a mutation where I cut out the C, then I would read them in 3s as well. The, ata, hunderte, he, at. Are you with me? So is the mutation good or is it not so good? So mutations are generally harmful. Even the ones that are so-called positives, like those that call sickle cell anemia, still make you sick. You get sickle cell anemia. It's a negative mutation. This slide over here of mutations has got nothing to do with mutations. It's just there to amuse you because I thought it looked cute.